Welcome to physics class. I hope you've been having a pleasant day. I just talked for 15 minutes and found out that I hadn't been recording, so I need to rewind and rethink this, and hopefully I'll be able to remember to say all the stuff. It was a great lecture, guys, so hopefully this will be just as good, and we're ready to talk about impulse and momentum. Okay, so if we're going to talk about impulse and momentum, you have to have an idea of what is an impulse and what is momentum. Impulse basically is a force that's applied to something, usually for a short amount of time, and there's a number associated with that. If you have a big force that's applied for a small amount of time, if the force is large enough, you have a large impulse. If you have a small force that's applied for that same amount of time, you have a small impulse. When you are playing tennis and you hit that ball, the time that the racket is in contact with the ball, it is delivering an impulse to the ball. When you take a baseball bat and you hit a ball that has been thrown towards you, you are delivering an impulse to that baseball for the amount of time that the bat is in contact with the ball. If you are stopping your car, you put your foot on the brake and you are delivering an impulse. You are delivering a force to your car for the amount of time that your foot's on the brake. So an impulse can change the motion of whatever it is that the impulse is being delivered to. Okay, the impulse can change the motion of whatever is being acted upon. It will possibly change the direction. It will possibly change the velocity. Okay, we can do our best to get a definition. It's a force that's delivered over a given time interval, and it's expressed by an expression. Okay, your book kind of dances around a definition for about 4 or 5 paragraphs, but I just summarized it in what I said. You've got force that's delivered over a given time interval, and it's given by the expression F delta t. Okay, delta because there's a change in time. There is a time interval. It is not instantaneous. Okay, this force is delivered throughout a given time interval, and it has a value. It happens to be a vector quantity because force is a directed vector quantity. Time is not, but when you have a direction with the force, that means that the impulse also has a direction. We are going to think of it as being a positive or a negative, and we will have to think in terms of setting up a coordinate system like for any vector quantity. And that brings us to the idea of momentum. You have an idea of what momentum is. It's used in common language. If something has a lot of momentum, it's going to be really hard to stop that thing. If something has a little bit of momentum, it will not be so hard to stop it. If something has a lot of momentum, it's going to be harder to get it off course, either sideways or from the front or from the back. Now, what we're going to be looking at is some equations dealing with just linear momentum, which just means forward or backwards. The circles and the sideways we will save for later on. The unit for F delta t for an impulse is a Newton second. Newton second, because you've got newtons multiplied by seconds. Momentum actually has a calculated value. It's the product of mass and velocity. How fast something is going times how much mass it has. So if something has more mass and it's going the same velocity of something else, it's going to have a bigger momentum. a train is going to have a larger momentum than your car. Okay, and everybody gets that law of physics. You get out of the way of the train, it has more momentum, even if it's not going very fast, because it's got a huge mass. Okay, however, everyone will also get out of the way of a bullet that has a tiny little mass, but it has a huge velocity, so it has a huge momentum, so it takes something to stop that thing. Okay, so momentum, product of mass and velocity. Momentum is given by the letter P. It is also a vector quantity. It has a direction to it. Something has a velocity, which is a vector quantity. It's multiplied by a mass, which is not. That means that there's a direction to momentum. The unit for momentum is kilograms times meters per second. Kilogram, meters per second, mass, and velocity. So it's got those couple of things that are going on. Now, an impulse will cause a change in momentum. So there is a theorem, which means it's been proved, that relates the impulse and the force multiplied times the time that force was applied and the momentum, or the change in momentum. This is applying to linear momentum, not in circles, because we don't have a way to bring in the angles into this particular equation. Okay, but the way this looks is like this. F delta t, which is the impulse, equals P2 minus P1, which is actually the change in momentum. So the amount of change in momentum equals what has happened because of the impulse, or the force that has been delivered to this thing. Okay, we want to look carefully at the way that looks. Impulse equals change in momentum. I want to take a minute to just show you, by analyzing the units, that this equation actually makes sense. So when we look at the units for both of them, F delta t is a Newton second. A Newton, if you remember, is mass times acceleration. So here's actually what the unit is for newtons that we can use the word Newton as a shortcut for. The seconds will cancel out, and it gives us a kilogram meter per second. Momentum, if you recall, is kilograms mass times velocity. Kilogram meters per second. So keep in mind that 1 Newton second is the same as 1 kilogram meter per second. Okay, that may not seem like such a big deal to you, but it really is pretty much of a big deal. And what students sometimes get confused about is that sometimes a question will ask you to find the impulse, and it'll very nicely give you a force and a time, and you just multiply them. However, sometimes a question will ask you to find the impulse, but it'll give you a mass and 2 velocities. And you might say, wow, how can I find the impulse then? I'm supposed to be using F delta t. But then you can use the other side of the equation, because they're interchangeable. Or a question may ask you to find change in momentum, and it's nice and easy because they give you a mass and 2 velocities, because remember, momentum is mass times velocity. But sometimes the question may ask you to find a change in momentum, but they give you a force and a time. But since they're equal, the words can pretty much be used interchangeably, and the calculations can be done with either side of the equation. Okay, so tuck that away in the back of your mind. The example I'm going to give right now doesn't use it in that way, but tuck it in the back of your mind anyway, because we are going to need to rely on that for some future questions. Okay. So let's take an example from the book. This example is found on page 203. And so I didn't make it up myself. I'm trying not to plagiarize. I'm just explaining where this example comes from. And it says, and I would like you to write it into your notes so that when you look back you'll have an idea of what the question was actually asking and what you found. 2,200 kilogram SUV is traveling at 94 kilometers per hour, which they've kindly done the conversion already for you, is 26 meters per second. And it can be stopped in 21 seconds by gently applying the brakes. That's how we all want to stop our car. It can be stopped in 5.5 seconds in a panic, or in 0.22 seconds if it hits a concrete wall. The average force, the question is, what is the average force exerted on the SUV in each case? Okay, there will be a force. The idea is, though, that that force is not always going to be the same. That force is dependent upon how long it took for that thing to stop. Okay, so let's organize some information here. Oops, I'm going to go the other way. Okay, we'll bring this up here. What do we know? First of all, we know the mass of the SUV. That's not going to change. Even when it hits the concrete wall, even if a piece or part flies off, we're still talking about the SUV as a whole. We know the starting velocity. That's pretty easy to find. 26 meters per second. We're going to use the meters per second value because all of the equations are using velocity, the standard velocity, which does turn out to be meters per second. The ending velocity is hiding, but it is in the problem. It says that it can be stopped. So the end result in each one of these three cases is that the SUV stops, and the stopping velocity is 0 meters per second. All right? And the change in time, well, there are 3 changes in time, and we're actually asked to do 3 different questions in this case. We're asked to evaluate the force during the 21-second stop. We're asked to evaluate the force in the 5.5-second stop. And we're asked to evaluate the force in the 0.22-second stop. So we have 3 things to consider here. So first of all, I'll bring this up. We're going to revisit the impulse momentum theorem. It's the impulse equals the change in momentum. We have a later momentum and we have an earlier momentum. So it's the later one minus the earlier one. Remember that P is m times v. So there's really 2, we're going to do the general stop one first. There's really 2 mass times velocity expressions here. This is your P2, your later momentum, and this is your earlier momentum. I've already gone ahead and plugged in the 21 seconds because we're starting with a general stop. So in the general stop we have this unknown force times 21 seconds equals these equal masses, because it's the same SUV, times the 2 different velocities. There's our 2,200 times 0, because this is our second velocity, minus 2,200 times 26. And as you do the calculations, 2,200 times 0 is just 0, and 2,200 times 26 is negative 57,200. And then we can divide both sides by 21, and you find out that the force is negative 2,724 newtons. Now, if that negative surprises you, think about it for a minute. If the original velocity of the car is in a positive direction, in order to get it to not be going in a positive direction, the force has to be in the opposite direction. We didn't have to calculate the acceleration. We did not have to calculate some of the other things that we did in the past. This is a fairly easy and straightforward equation. Okay, so the change in momentum is going to be the same for all three time scenarios. Time is not part of the change in momentum. So that means when we do the other two problems, the 5.5 second problem, and we do the 0.22 second problem, we're going to be able to borrow this negative 57,200 because the change in momentum is the same in all three cases. The same thing happened. It ended at 0 and it started at 26. In all the cases, it just took a different amount of time to do that. So let's take a look if we now are going to look at the panic stop. Okay, the panic stop. So the panic stop, we have, again, F delta T, but our T has changed. Our T has changed to 5.5. But our momentum is the same. The momentum is still negative 57,200. So negative 57,200. So what we need to do to calculate is divide by the 5.5. Keep in mind we're dividing by a smaller number. So dividing by a smaller number, you're going to expect that the force is going to be a greater number. So let's do this. Let's do 57,200 and divide it by 5.5. So what we get now is 10,400, negative 10,400. It's still negative. It still has to go in the opposite direction. But it's much bigger. The magnitude is huge now. Negative 10,400 newtons. So there's more force applied to that car. The brakes had to do more to slow it down when it had to slow down more quickly. Okay? But what about with the crash? Okay? In the panic stop, there's no damage to the car. In this, it's a nice gentle stop. There may be a little damage to the tires. They might have generated some heat in the doing this. But let's take a look at the crash. Now we have F, and the delta T is 0.22 seconds. Still, the same change in momentum happened. But now, when you divide by the time, we're dividing by a much smaller number. So 57,200, when you divide that by 0.22, we're now getting 260,000 newtons. So we've gone all the way from 2,700 to 260,000 newtons. And all that force causes crumpling on the car. It causes damage. It causes injury. So the greater the force, the more the car has to actually deal with. Okay, so this force is way more when it hits the wall. The result is the same. The momentum had to change this much in all the cases. The change in momentum was the same, but the actual force involved was very, very, very different depending on what was going on. Okay, so now that actually is a fairly advanced question, but then we backtrack to some of the simpler questions, and traditionally people aren't really quite sure what to do with them. Okay, so let's backtrack and do some simpler questions so that you can be prepared to do some of the homework. Okay. Let's say that we have a 500 kilogram mini car. And that would be a tiny car that is moving at 75 kilometers per hour. Okay. And we want to find its momentum. Okay, so, and then afterwards we want to find the momentum of an SUV that is 2,300 kilograms, or find, sorry, not find the momentum, find the speed of an SUV that is 2,300 kilograms if it has the same momentum. Okay, so let's take a look at this. First of all, we have a problem. We have 75 kilometers per hour, and our calculations are supposed to be in, hopefully you said meters per second. Okay, so we need to do a little bit of a change. We have 75 kilometers per hour, so we need to change that to meters per second. Don't forget there are 1,000 meters in a kilometer, and there are 3,600 seconds in an hour. So basically what this means is that you're going to take 75 and by canceling out divide it by 3.6, and we get 20.8, so about 20.8 meters per second. Alright, so this car is going at 20.8 meters per second, so its momentum, P, equals, think about the momentum equation, P equals m times v, which equals 500 times 20.8. So let's do the answer that we got here times 500. And so the momentum of this mini car is 10,417. And our unit kilogram meters per second. The velocity of the SUV, that's 2,300 kilograms if it has the same momentum. Same momentum. So we have to think about, well, what do we do with that? You still have P equals mv. P is the same value that we just found, 10,417. So 10,417 equals different mass, 2,300, times the velocity. So you need to divide that 10,417 by 2,300. And that would give us a very slow velocity for that SUV. To have the same momentum, it's only going to have to be going 4.5 meters per second, which is super slow. Alright, so its meters per second is like that. Now, if we wanted to, we could actually convert. So let's do that. Let's convert that so that it's something we can understand. 75 kilometers per hour is even maybe a little bit beyond what we can understand, but look at your speedometer a couple times and you'll kind of get the hang of that. But let's find out what 4.5 meters per second is in kilometers per hour. So we do the same thing but backwards. We have 1 kilometer and we're trying to cancel that out with 1,000 meters. And we have an hour, which you're trying to cancel out with the 3,600 seconds. So basically you're taking 4.5 and multiplying it times 3.6. And we end up with 16.3. 16.3 kilometers per hour. Alright, now, if it doesn't say convert in the question, you don't have to. It's just, it sometimes helps to be able to really get a handle on what makes sense in a problem. Okay. Now, a lot of the things in your book are going to tell you to sketch before and after diagrams. Sketch them if you need to help you make sense of the problem. But do keep in mind that if something slows down, then the velocity will be negative, and you just have to keep in mind your positives and your negatives. So a slowing down object, if you're saying it's going in a positive direction, a slowing down object will have a negative force applied to it. If you have something that's going to speed up, then you're going to have a positive impulse applied to it. Okay? Let's get one more example in for the day, and then we'll actually, hopefully you need to start doing a problem or two here. Okay. So let's say, oops, let's say your $16-kilogram dog is moving at 10 meters per second. Okay, suddenly it sees a car coming and stops in 1.5 seconds. Okay. find the force on your dog's feet. Okay, so let's do that. So once again, we have our impulse momentum equation, F delta t equals P2 minus P1. So F delta t, the force, is actually unknown. And that's what we're supposed to be finding. But we do know the time. We know the time is 1.5 seconds. Our later momentum is made up of m2 times v2. So this is later. Later in the problem, the dog has stopped. So the mass of the dog, 16 times 0, minus P1. So this is earlier. Earlier the dog was going 10 meters per second. Mass, 16 times velocity, 10. Okay, so F times 1.5 equals negative 160. So the force on the dog is negative 160. Clear all this out. Negative 160 divided by 1.5. And we get about 107 newtons. Okay, force on your dog's feet due to friction. We could be a little bit more careful on that one. But once again, these equations, they work out very well. You just have to be very careful as far as what you're asked to find. What I would like you to do now is, right now, I want you to work on problem number 1 right here in class before you leave. So take out your book, do problem number 1. It's just like that first example that I showed you, but I want to make sure that you've gotten it before you leave. And tomorrow, make sure you come in ready to learn more about impulse and momentum. Have a really blessed evening.